So welcome everyone to our presentation today. We are going to present store-to-leak forwarding there and back again. My name is Claudio Canella. I'm a PhD student at Graz University of Technology. You can also find me on Twitter or send me an email if you have any questions.
My name is Lukas. I'm also a PhD student in Graz. Don't be thrown off by the shirt. Some below this later. You're exactly where you're meant to be.
And my name is Schwarz. I'm a faculty at CISPA Helmholtz Center for Information Security. And you can reach all of us on Twitter, via email if you have any more questions, more than you could ask after this talk. So what is this talk about? So we want to figure out in this talk how stores and loads are handled on modern microarchitectures. What happens if we load a value from a location where we previously stored some value? We also want to look at the Meltdown mitigations and see what they changed in this store and load path in the microarchitecture, and see whether we can figure out some new mechanisms from that allows for some new attacks. And of course, we also want to mitigate those attacks that we find, so we'll also talk about some clever mitigations here.
Okay, so first we need a bit of background. So the mental model you can have as a programmer from the CPU is fairly simple. So instructions are executed in program order, just as you expect, just as you write them down. The pipeline stalls when the stage is not ready. And if data isn't available, we also have to wait. So this can look something like this, where we first fetch into the L1 instruction cache. We decode the instructions, then we execute them. If necessary, we perform accesses to memory. And finally, we write back into the architectural register file.
I always thought that microarchitectures are much more complex than that.
Well, that is a very simple microarchitecture. And in general, in modern architectures, you want more performance, and more performance means superscalar. And superscalar means that we do loads of things in parallel. So the question here is, if we don't have a dependency between different instructions and we have many execution ports available, why don't we do loads of things in parallel? So we execute them in whatever order is convenient and the ports are available. And importantly, we retire them in the order that they're in the program. So from the outside, from a programmer's view, everything still stays the same. So now an interesting situation is when a fault happens and there are already newer instructions in flight that are already calculating on data. What do we do with them? So for this, the processor tracks the architectural changes that instructions would make, and if there is a fault, it undoes the out-of-order effects, and we then call those instructions transient.
That's pretty smart.
Yeah, it is. And those transient instructions don't leave any architectural trace. They're basically gone. So at this point, you might wonder, if they're undone, if they don't leave any trace, what are they even for? What's the point of them? Or what can we do with them more as an attacker? And so remember I said the processor tracks the architectural changes and reverts those. It does not track microarchitectural changes. So we can encode data that we calculate during transient execution into a microarchitectural state.
Do you have an example for microarchitectural state?
Yes.
I don't know what you're talking about.
Yes, I do. One of those stateful microarchitectural elements is a cache. That's a simple way. And so the state in the cache is if a cache line is present or not. And so let's have a look at an example. We access a variable and try to load it into a register. And so the first time we try this, the CPU will have a miss. And it will have to load from RAM, we'll get a response, and it will be cached at that point. And the next time we try this...
Sounds slow.
Yeah, and the next time we try this, we get a cache hit, and that'll be much faster. So the DRAM access is very slow. The non-DRAM, the cached access, no surprise here, is much faster. And this difference is very clear, and we can determine this with high reliability. So in the future of this talk, when we talk about transient instructions and their effects. This is how we generally see them architecturally, how we make use of them. We encode them in the cache. So when we look at how a core is made up, we've talked a bit about the execution engine, the front end. So what's left is the memory subsystem. And so here first we have a load buffer and the store buffer connected to the load ports and the store ports in the execution engine. As a next level, we have the L1 data cache with a TLB and line fill buffer. With a second level with the L2 cache and another TLB. And then off-core, we have the L3 cache and the RAM finally. And so these three caches are what we can use, as just said, to encode our transient data. So
wow, that looks complicated.
Yeah, so why don't you tell us a bit more about the store buffer?
Okay, so let's see what actually happens if we have some data stores and data loads that we are executing that has to go through all this machinery you just explained before. So if we move some data to the memory, so if we store some data, then what happens is that in the execution unit, we have the store operation. It has to store some data, and for that, it uses the store buffer. The store buffer helps that it does not have to wait for the store to actually complete. It just throws it in there, and then the store buffer handles the rest of it. And the store buffer then can go to the L1, store the data in the L1 if there's space in the L1. And in the meantime, the execution unit can already continue with some other instruction. You've said that before with this out of order execution. So now we do something maybe stupid. We write some data to memory, and then immediately afterwards, we read from this memory address the data back that we just wrote. We of course know what this data is, but what does the CPU do? So the CPU, for loading a data, it uses this load data part in the execution unit, and it uses a load buffer, where it also has a kind of a queue where it stores what values to load. And it knows this address, it has to load that, and usually it would go to the L1 memory, check the L1 memory, is this data there? If there's a hit, then retrieve it. Otherwise, go to the L2, L3, or DRAM. But the thing is, CPUs are quite smart nowadays. So what this additionally does, it checks whether some address was already stored before, some data stored to the same address. So if there's a match between the store address and the address that we load, we can do a shortcut. We don't have to wait for the memory. So we directly take it from the store buffer and do the store to load forwarding to this load. So this is a lot faster. So we have this data that goes there into the execution unit memory subsystem and then back again before it even reaches the memory subsystem, that the L1 or L2. So this makes it a lot faster and is a nice optimization that we have in modern CPUs. Of course, we can optimize that further. So we don't have to check for a full match. We can optimize that even more. So we can do something like a normal comparison. And if it's true, we do the forwarding, and this can be okay. So it's a true positive. Everything happens as it should. We only forward the things that actually match. Maybe we also have some errors in the comparison there because things go really fast, and we might have other stores and loads in between. So maybe we also have some true negatives where we don't have something there, and we're not matching anything, we're not forwarding anything. That's also fine. That's true negatives. And this is basically all true positives and true negatives that we exploit in this talk here.
But wait a second, that sounds familiar. Yeah. Isn't there a second attack that does exactly the same? Isn't there Fallout?
Yes, because these are not the only two cases in the store buffer. We can also have some, let's say, kind of errors or optimizations in there, like false positives. So we have addresses that are actually not the same, but the data is forwarded. So this one is exploited in Fallout, but already fixed in modern CPUs. And then there was also the other direction. like false negatives, the address is actually the same. It should forward the data, but it doesn't do so. And this effect is exploited in Spectre STL. So all these store buffer magic in there are optimizations for the transient execution. So for the parts we don't see, if this optimization is wrong, architecturally, we don't care because everything is undone, as Lukas explained before. So we will never see that. And our attack here just relies on the store buffer to do everything correctly. So correct matching, correct forwarding on the same addresses. One interesting part here that we are going to exploit is that stores can only be forwarded if we store something to a valid address. Of course, that sounds kind of intuitive. We can't store somewhere that's not a valid location. So this is also described in the Intel manual. So it says like the store execution phase, it fills the store buffer with linear and physical address and data. And once store address and data are known, the store data can be forwarded to the following load operations that need it. So if everything is known, then we can forward this data to the load. And what does it mean with valid and invalid? A virtual address that has an actual physical backing to it. So we have some data page where we can really write to it, then this is a valid address. And then we can use that. The interesting thing that we already know from Meltdown is that permission checks on Intel CPUs are a bit lazy and they're not done up front, but at some point in between when we already do that. So that's what that was exploited in a Meltdown attack. And we want to exploit the same thing. What happens with this store to load forwarding when we store some data to an address and then read it back, but this address is inaccessible. So it's still valid. There's a physical page behind it, but maybe it belongs to the kernel, so we couldn't access it. Does this mechanism still trigger? So let's try. It's not that difficult. We write some value onto a kernel address. That of course gives us a fault, a segmentation fault, but out of order execution instructions are still executed. So in this out of order execution, we read the same address back, encode it in the cache as Lukas explained before, and see if we get the same value back. If so, we know that it's store to load forwarding that's actually working, although there was a fault.
So that's nice and all, but what does that get us? What can we do with this?
That's a good question. I bet you've heard about address space layout randomization. Especially in the kernel, we have that, so we randomize all the parts in the kernel, the modules and the kernel image, and every time we boot, it's at a different location. So the modules are at different locations, the kernel image is at a different location, so we don't know where the kernel is, and so we can't mount reliable attacks on the kernel because we don't know where the image and the data is located.
Okay, but with this explanation, I think I know what your attack is that you want to do. So I think it's called data bounce. We can see here we have, again, a memory subsystem with the store buffer and the load buffer. We have a little bit of code, and the blue square here indicates the location of the kernel within memory. And mem here is just an array where we store data. And if we time this right now using the primitive that Lukas told us, then we just see the timing is always the same because we need to fetch it from DRAM, right? So now what we do with this store to load forwarding logic is we simply write to a kernel address some value, in our case the value x, and later on dereference it, use the value that we get back from the kernel address as an index to our memory, and then we should observe this x if the store to load forwarding logic works. So let us try this. So in the beginning, there's nothing mapped. So as Michael said, we cannot write this. There's no store buffer entry for this. So we don't find anything. We can repeat this and we never get a value back. But now we find the location where the kernel is actually mapped. And suddenly we can write to this address we get a store buffer entry. When we load then from this address, we get the store to load forwarding effect. We get it into the load buffer, and the data is forwarded and used in the subsequent instructions for the access to mem. And if we then use our primitive again, we can suddenly see that the access time for X is much slower, and we know that there is something mapped. Our kernel is there. So the question then is, what if an address is valid but unknown? So we know it has a physical backing, but it's maybe not in the, we don't know the physical address yet because it has not been used recently. So what if we simply repeat data bounds? We can see here we have unmapped regions, we have mapped regions as well. If we get our data and in the first try of data bound, so it's forwarded on the first try, we know that this in the DLB, so it has been recently used because we know the physical address. If we get it on the second try, we know it's valid, but it's not in the DLB. And in the final case, we don't get any forwarding no matter how often we try it. Then we can infer that this address is unmapped. It's not valid.
That's a nice observation, Claudio. But I don't think it has any security implications. I mean, what are you going to do that? We already broke KSLR. What are you going with that additional information?
No, I think we can do something. I think there's an attack primitive here, and all good attack primitives need a name. So I think we're going to call it fetch and bounce. So now we aren't agnostic of a TLB anymore. We know it's there and we use it. So in this case, we see 4 kernel pages that are all mapped. And now what we're going to do is we're going to do it again, but with fetch and bounce, we only access once each. We don't repeat. And so when we do this for the first address, we can see that we get a lookup in a TLB. There's nothing there. And so when we try to store, we can't get a valid store buffer entry. And so we also can't get forwarding. And so now there's a TLB entry, but it's already too late. We've moved on to the next address. And the same thing here. TLB is empty, there's no entry. Again, we don't get a store buffer entry. So now, but for a third address, there is already a TLB entry. And so when we try it now, we get a store buffer entry, we get forwarding, and in our next address, we get the X back. And so now what we've learned is that recently this page was actually used by the kernel. And so that's a new attack primitive here. For the last page again, it's not mapped, and so we get nothing back. Okay, so what can we do with this? We can observe kernel activity, and more specifically, for example, something like the modules. We can check which module is used and which code page in it is used. So as an example, we use a Bluetooth module, and maybe we connect our phone to it and play some music. And then we can detect when there is some activity here. Okay, so...
Does that really work?
It does really work.
Or is that just theory?
It seems a little bit far-fetched. So can you show us that this works? Because I don't.
Okay. All right. Let's go into detail a bit more. So the first thing you have to solve is we don't actually know where the modules are because they're also hidden by KSLR. And so unlike the kernel, we might be able to find them, but we need to do some more to identify them. And so what we do is here in this demo, we scan the entire module address space. As you can see, that's very quick. We identify contiguous pages of memory, and we can infer that those are modules. And we can read the size of the module with that. And so now we can match unique sizes to modules with unique sizes. So here we've identified 3. We're going to check in proc modules if the addresses are correct. So we're going to check for Bluetooth. That looks correct. We're going to check for the Wi-Fi module that we tried to identify. That looks good as well. And lastly, the Thunderbolt module, we also correctly identified. And you can also see that the found sizes match because the sizes, again, are how we identify the modules. So this doesn't work for modules of the same size. So that's the first step. We know where our target module is, in this case, the Bluetooth module.
So what you've basically shown us now is that this is data bound.
This is data bounce, right? This is data bounce.
You still haven't shown us that fetch and bounce works.
Correct. Let's use fetch and bounce with this. Now we know where the module is. We know an address, let's say some page in a Bluetooth module we want to attack. And so now what we're going to do is we're going to sample with fetch and bounce this page in a Bluetooth module. Then we're going to clear the TLB for this core because the TLBs are per core and not shared. Then we're going to jump to the next core and do the same thing. And so with this, we move through the cores in order and give the Bluetooth module time to work, and then we sample again. And so this is what it looks like in action. We get hit rate. And you can see as soon as we hit play on the right on the phone, we get correctly identified ones. And so for the Bluetooth module, something we've noticed is that there is some after activity. So now we get zeros again. We're going to start. And we get a very sharp identification here again. So you can see right now, we have about 1% of detection, which is because of that's how often we sample. So again, you can see that the temporal resolution for first detection is fairly good. In this case, we just don't do this very often. And you can see this is all very stable. And in general, from the music, you get that this is a very important POC. This is very dramatic. Right. So it works.
Okay, yeah, I believe you.
All right, we can do something with that.
That's a great demo.
Thanks. So
Thanks.
We have something else as well, though, another variant. But for this, we're going to have to go a bit back in time. And Michael is going to tell you a bit more about that.
Exactly. I was just thinking, so you talked about out of order, transient executions and stuff. What if we actually combine that with another transient execution attack that we know, Spectre? So if we just short recap for Spectre, it's about, the variant 1 is about bounce and predicting bounce of accesses. And if the CPU predicts that something is in bounds, if you do an in bounds check, then everything is faster because it was predicted correctly. If there was a misprediction, it might be a bit slower, but it's still okay. If it predicts that's not in bounds and is actually not in bounds, it's also fine. The prediction was correct. But there's one corner case that is actually exploitable, the Spectre attack. So if the CPU predicts that something is in bounds, but it's not in bounds. So that means we can transiently access data out of bounds of an array. And if you look at the simple if condition here that checks whether an index, a given index, is smaller than 4, and then accesses an array that has 4 elements, and after this array there's some secret data in memory that we shouldn't be able to access architecturally because we have this bounds check here in the if condition. And it uses this data here as an index for some memory, for example, a font file here, to do pretty printing of this letter that we get from the array. So if we look at that, the first time the CPU has no idea if this condition will be true or not. It speculates something, maybe it speculates for it's wrong. Okay, nothing happens. Then if we actually execute that on a CPU, the CPU sees, oh, this condition was actually true because 0 is smaller than 4, and it loads the first value from memory. It uses that to index this font file that we have here, and all of that is put transparently into the cache. And the next execution, we have the next index. 1 is smaller than 4. The CPU is like, oh, it was smaller before, it was true before, so let's speculate that it's also true now. It speculates that it has to get the data from memory. It does that, looks it up in this font file, everything is put in the cache, and when it actually executes it then, architecturally it says, oh, my prediction was correct, everything is fine, nothing has to be undone, perfect, super fast. And it continues like that for the next index and for the next index, and then we get to index 4, and 4 is not smaller than 4. But the CPU is like, yeah, it was always true, this condition will be true as well this time. So it starts fetching memory that's actually out of bounds of the array. So it shouldn't be accessible, and takes that, looks it up in the font file, puts it into the cache, and there we have our problem. We have something in the cache that correlates to the secret data in memory that we're not supposed to access. And as Lukas said before, we have these attacks that can measure the timings, and also Claudio exploited that. And we can see that from the cache, and infer the secrets from that. And now we could also combine that with our fetch and bounce method. So if we have this bounce check here, this condition, and then we could access something based on this index here, then it's not only put into the cache, but also into the TLB. So then we can use fetch and bounce to iterate over the memory. Instead of doing a cache attack, we're doing a TLB attack with fetch and bounce, and we can infer that secret from the TLB, whether it was a TLB hit or not, so whether fetch and bounce succeeded at the first try or not.
That's very interesting, but I remember there was Spectre, and wasn't there another vulnerability as well that, I don't know, it sounded really scary, something like nuclear stuff.
Something like that.
Ah, you mean Meltdown? Yes. Meltdown was also at the same time, but it's a different attack. So this exploits the permission check that we also exploit here with data bounce, so that permissions are checked later on. And with that, it was possible to basically read the entire memory, because even inaccessible memory could be accessed transiently, encoded somewhere, and then restored with a side channel attack. And as the kernel maps all physical memory, basically we can read arbitrary memory with Meltdown. So yes, you're right, super scary.
Yeah, but I mean, we know it's scary, but how do you fix this? I remember that there was like this huge performance impact. So isn't there a smarter way to fix this?
Right, so we know that Intel did fix it, but we don't really know how, right? So let's reverse engineer this. Let's see. We make a few assumptions here. So stalling the CPU, we think, might be a bit costly. And it might also require some re-engineering of the pipeline. And we know that these mitigations were rolled out fairly quickly. So let's make a guess here. Let's say data is just zeroed out on a load if that load falls, but the load still happens. So we can test this hypothesis. So first, we just do Meltdown. And Meltdown, unsurprisingly, on mitigated CPUs now returns 0 and not the data anymore. So that's good. Mission accomplished, right? So we confirm our hypothesis of how this works with some performance counters. So first we look at memory stalls, and we compare Intel CPUs that are vulnerable, that are mitigated, and an AMD CPU. And so what we can see is that on a vulnerable CPU and on a mitigated CPU, for user and kernel accesses, there is the same percentage of stalls. That is not 100% like it is for non-present. And on an unaffected CPU, such as an AMD CPU, we see that non-present pages and kernel pages both stall 100% of the time. So we can look at a second counter, the issued microops on the load ports. And again here we can see that with and without mitigations, user and kernel address accesses have the same number of microops issued. And that again points towards our conclusion that loads still happen in the background, they're just zeroed out. And so just to be sure, we try the third measure. That is when we have an access that misses the L1, we measure this, we look at this mispenning cycles counter. And again, we see that between unmitigated and mitigated CPUs, the ratio of user and kernel accesses is exactly the same. So again, this leads us to the conclusion, it's just zeroed out, the load happens in the background anyways.
So that's very nice, but when I see this, I immediately think that, can we use the hardware-based mitigations for an attack? Because it sounds like we can do that.
Why don't you build one?
Well, we've seen already KSLR breaks, we've seen data bounce, which was such an attack. And when we've looked at these mitigations, we thought, okay, we find another one, let's call it EchoLoad, which is a very fast and reliable KSLR break. And it again simply encodes the returned value when we access it, simply like a Meltdown attack in the cache. And EchoLoad, for instance, it can be summarized with this very short sample of code. It's more or less a memory access encoding data that we load from the kernel address.
And that looks almost the same as before, so
yeah,
what's different now?
But it's a little bit different, because what we here exploit now is that we exploit this stalling behavior when the CPU tries to access the memory that is not backed by physical memory.
I see.
So we can change this kernel address and we never find we always stall. But at one point, we get to this location where the kernel is actually placed, and now we see the effect that these mitigations have, because now we have a faulting load and we get a 0 back. So we know now where the kernel is placed. Nice, right?
That's pretty cool.
But the question then is always, what's the performance of EchoLoad, right? Because that's what we care about.
In the end, we want numbers, we want speed.
Yes. And we evaluated it on several CPUs with mitigations, without mitigations, because it also works on those without mitigations, because then it's simply Meltdown. Right. And we also tried it because we have a faulting load, so we need to somehow prevent our program from dying. We placed the faulting load within speculation, within TSX, which is an Intel feature, or simply by using a sec fault handling. And as we can see, it is very fast on the i9. With TSX, we have like 29 microseconds and a perfect accuracy with an F-score of 1. So we are very reliable and very fast, even faster than previous state-of-the-art. And for the other CPUs with speculation, we sometimes see that it's not completely perfect, but this is more or less because inducing speculation doesn't work always reliable. So this might be the explanation for that. What we were also able to do is we were able to show that this attack works in SGX, and we can also use it in JavaScript. So now, in the beginning, we talked about that we not only want to attack something, but we also want to defend against these attacks. And we need a software workaround for that. And we don't just want to mitigate data bounce or EchoLoad. We also want to mitigate other attacks that have been designed previously. And so in order to do so, we need to come up with what are these attacks exploiting. So we looked at all of them, and we discovered that they all exploit timing differences between mapped and unmapped pages, like we saw just now with EchoLoad and data bounce, for instance, as well. There has been another attack that simply differentiates the kernel based on the different page size it uses. And there's another one that can differentiate the timing difference between executable and non-executable pages. So if you want to prevent all of these attacks, what we need to do is we need to mitigate all of these attack vectors. So our mitigation is called FLARE. It stands for Fake Load Address Response. And we can see here the current Linux design without FLARE in place. And we have the beginning of the kernel is somewhere randomly placed with KSLR, and the code section is directly followed by the data section. So code is obviously mapped using executable pages, and the data section without. So we need to prevent this. In the first step, let's take look at the mapped and unmapped pages. We simply fill out all positions where the kernel can be mapped. Quick and easy solution, right?
Of course. And we're done now, right?
And more or less. So we fixed the data bounce on EchoLoad, for instance, but others are still problematic. So in this step, what we also need to do is we need to ensure that all of them use the same page size. So all of them use 4 kilobyte pages, for instance. In the next step, we mitigate the difference between executable and non-executable pages. So we simply split the range for the kernel, place executable code in the first half and non-executable in the second half. So the switch now is always at the predefined location that the attacker already knows. So with this simple fix, we've fixed all of them. So how does this now look if we, for instance, perform FLARE? We've seen this before, but now everything is mapped and we always get 0 back.
So that's EchoLoad, right?
That's EchoLoad now, right? So when we take another look at all the other attacks, we have seen EchoLoad already before. Prefetch, this is the one that was able to differentiate the different page sizes. We can see here unmapped 1 gigabyte, 4 kilobyte, and 2 megabyte pages. With FLARE, there's nothing there anymore. Data bounce, we've already seen that one, also not differentiable. The double page fault simply tries to access something twice and measure the timing difference, because if it's mapped, the second access will be fast. Also not possible anymore. Dr. K improved the double page fault by using TSX, so we also don't see it there anymore. And Fallout is also hidden, and Michael already discussed the difference between Fallout. So we also implemented this as a proof of concept, which you can find on our GitHub page. check it out. We don't take any guarantees that it works flawlessly, but
It might break your system.
Probably
won't.
Never happened to me. So yes.
All right. So what do we take from that? So we see again, optimizations, whatever they are in a microarchitecture, they introduce security problems.
And sometimes these mitigations can fix the main problem, but there can still be some edge cases that are overlooked and are still exploitable.
And we've seen that once again, just like with Meltdown, we require software mitigations to prevent these edge cases. With that, we are more or less finished with our presentation, and we hope you enjoyed it, and we are looking forward to any questions that you have.
Thanks for your attention.